Imagine zooming into an image and discovering that no matter how far you go, new patterns continue to appear.
First, this may seem impossible, but mathematics are full of surprises, hidden within natures, from trees to lake, rivers, and lightning are all patterns that repeat itself. These patterns are called fractals. Here, we will explore what are fractals, why they are so fascinating, and how they reveal the unexpected relationship between mathematics and the world we live in.
The hidden mathematics of nature, exploring fractals in nature and daily life. Table of contents. 1. Introduction. 2. Understanding fractals. 3. Fractals in nature. 4. History of fractals. 5. Property of fractals. 6. Types of fractals. 7. Real-world application. And 8. Conclusion with some fun facts. Introduction. Mathematics is far more than just numbers and equations. It can even help us understand nature, technology, patterns, and even the universe. But one of the most beautiful and interesting topic of mathematics is fractals. But what are fractals? Fractals is a pattern or shape that repeats itself at different sizes. Now, this property is called self-similarity. Fractals are often created using simple mathematical rules repeated many times. Examples include lightning, snowflake, trees, rivers, and even quantum material. Now, moving on to fractals in nature. Fractals naturally appear in nature, such as trees, lightnings, and rivers. Now, this is a tree bark. Tree bark often forms repeating crack and rigid patterns that resemble fractals. As the tree grows, the bark expands and breaks into similar shapes at different scales, showing how mathematical patterns naturally appear in nature. Another example we have is river systems. Now, river systems form branching patterns where smaller streams repeat the shape of the larger rivers. These repeating structures are also an example of fractal geometry, naturally occurring in nature. The third example is our blood vessels. They branch into smaller and smaller networks and repeating patterns, forming a fractal structure that helps efficiently deliver oxygen throughout the body. Our last example we have is lightning. Lightning forms branching patterns that repeat at smaller scales, making it a natural example of fractal geometry. These shapes shows how energy travels through a path of least resistance, creating ordered pattern within seeming chaos. Now, history of fractals. Fractals have become very famous through a man named Benoit Mandelbrot. Benoit Mandelbrot was a Polish-born French-American mathematician who revolutionized geometry through his work on fractal geometry. While working at the IBM, he used powerful computers to study patterns created by simple equations and discovered the Mandelbrot set in 1980. By repeatedly calculating the equation below, he found infinite complex shape with self-similar patterns. Now this is the formula he discovered, z equals z squared plus c. Mandelbrot showed that chaotic and irregular forms in nature, such as clouds and coastline, could actually follow mathematical rules. His discovery changed how scientists understand complexity in nature and inspired the idea that many structures in the universe, from galaxies to neurons and DNA, may contain repeating fractal patterns at different scales. Moving on with an example below. A computer is creating a fractal firework display. To decide whether a spark stays in the shell, it uses the Mandelbrot rule. Each round, the computer calculates a new value of z. Z equal to z squared plus c. Now this is a more specific formula, zn plus 1 equals zn squared plus c. We use this formula to solve examples in the word problem rather than using just a regular z equals z squared plus c. So questions. Calculate z1, z2, and z3. If a spark disappears if z becomes greater than 2, during which iteration does the spark disappear? The conclusion or the answer. The computer starts with z0 equals 0 and c equal 1. Now c equal 1 is a fixed number, so c is always going to be equal to 1. Now we start with z equal to 0. Now z0 equal to 0, or you can write z equals 0. Step 1, we're calculating z1. Now if we use the formula zn plus 1 equals zn squared plus c, zn would be equal to 0. So z1 would be z0 plus 1 or equal to z1. So z1 equal to z squared or zn squared. Now we know that zn equals 0, so we can just write z squared plus c. So it's equal to z0 squared plus 1 equal to 1. So z1 equal to 1. Now step 2, z2 equal to z squared plus c. Now z2 would be equal to z1 plus 1 equal to z squared plus c. We can write z1 squared plus c, so z1 equal to 1. So it's 1 squared plus 1 equal to 2. repeat it with step 3 to find z3 equals to z2 squared plus c would be equal to 2 squared plus 1 equal to 5. Now, since 5 is greater than 2, the spark disappears at the third iteration. So, z1 equal to 1, z2 equal to 2, z3 equal to 5, and the second question they ask, when does the spark disappear? So the spark disappears at the third iteration. 2. Properties of fractals. Fractals have many properties such as its self-similarity. Smaller pieces resemble the entire shape. For example, if you look at this branch of tree, the branch of the tree looks like a smaller version of the whole tree. Another one is fractional dimension. Fractals can have dimensions that are not whole numbers, they are more complex than normal geometric shapes. Generated by simple rules. As we've learned below in the Mandelbrot set, complex fractals can just be created using some simple equations such as the z equals z squared plus c. Now moving on to types of fractals. Another type of fractals we have is the Sierpinski's triangle. The Sierpinski's triangle is a famous fractal pattern that takes the shape of an equilateral triangle nested infinitely within smaller triangles. Now, to find how to make a Sierpinski triangle, we have to simply connect the midpoint of an equilateral triangle and color in the upside down triangle in the middle. You can then continue the pattern for each of the newly created triangle for as long as you like, or for as long as you can keep fitting smaller triangles inside. The pattern goes on forever and ever, now thus making it a fractal. Another type of fractals we have is the Koch snowflake. The Koch snowflake is created by repeatedly adding smaller triangles into each side. Now we start how to make a snowflake. We start with an equilateral triangle, then we add another equilateral triangle on the middle side of each side. We pull out the middle and repeat the process this time with 1, 2, 3, 4 times 3, which is 12 sides. We do this over and over and the shape will look something like this. Now, this is called a Koch snowflake and it has special properties. No matter where we look or how much we zoom in, we will always see the same pattern over and over. Never adding patterns like this on any scale or on any level of zoom look roughly the same. Now, we can actually draw a Koch snowflake on the computer by having it graph a mathematical equation. Each time we add a triangle onto one side of the Koch snowflake, it will turn into 4. After the first repetition, we'll get 3 times 4 to the power of 1, or 12 sides. After the second repetition, we'll get 3 times 4 to the power of 2, or 48 sides. If we do this an infinite number of times, we'll get an infinite number of many sides, so the perimeter of the Koch snowflake will be infinite, but the area of the Koch snowflake wouldn't be infinite. If we draw a circle with a finite area around the Koch snowflake, it will fit completely inside no matter how many times we increase the number of sides. So the Koch snowflake, or the Koch fractals, has an infinite perimeter but a finite area. Now, moving on to some real-world applications. How can fractals be used in our real world or in our daily life? So, antennas. Nathan Cohen used fractal shapes to create smaller antennas that could receive many different signals at once. Unlike regular antennas made for one signal, fractal antennas are compact and multi-purpose, though harder to build though. So, he built the first working fractal antenna by Nathan Cohen at 1988. Fractals can also be used in medicine. Doctors use fractals in real life to better understand and diagnose the human body. Many natural structures such as blood vessels, lungs, and brain cells have branching patterns that we discussed earlier about the blood vessels that resemble fractals. It resembles fractals. By studying these repeating patterns, doctors can detect diseases, analyze medical image, and monitor how organs function. For example, changes in the fractal patterns of blood vessels can identify heart disease. This shows how mathematical plays an important role in modern medicine. Now, weather prediction. Fractal geometry is used in weather prediction because many natural weather patterns such as clouds, storms, and rainfall have repeating fractal shapes. Scientists study these patterns to better understand complex atmospheric behavior and improve computer models that help predict weather more accurately. In weather prediction, fractals are used to study cloud formation, hurricane and storms, rainfall patterns, and turbulence in the atmosphere. Moving on to our conclusion. Fractals show that mathematics is hidden everywhere. In nature, simple mathematical rules can create infinite complexity, beautiful patterns, and natural structures. Fractals are where mathematical nature and infinity meet. Fun facts. Fractals can continue infinitely. Some fractals have non-whole number dimension. Nature naturally creates fractals, and fractals combine beauty and mathematics.
Fractals show us that simple rules can create extraordinary complexity. From mathematical model to natural phenomena, it reveals patterns that repeat itself across different scales and help us understand better in the world we live in. The more we look, the more we discover. And perhaps that's what makes fractals so fascinating.